Okay, so in this problem we'll apply all the concepts that we learned in the previous video. Okay, so you're given 3 moles of a helium gas. The molar mass is 4 grams and it's at a temperature of 27 degrees Celsius. Now the first question is determine the average kinetic energy per particle. Okay, so we'll go back to our formula. So average kinetic energy per particle is equal to 3/2 times kb times T. Now here the temperature has to be in Kelvin. Okay, so we're going to do 3/2 then 1.38 times 10 to the minus 23 and multiplied by the temperature in Kelvin, and I'm just going to approximately write this as 300 Kelvin. Okay, so if you want you can just do 300.15 and then you can obtain a value for the kinetic energy. Just make sure calculate it and see what you get. Okay, the next part of the question is determine the internal energy of the gas. Okay, now to answer this question, we'll use a simple relation that U is equal to 3/2 times N times R times T. Now you've been given the number of moles, so it'll be 3/2 times 3 times 8.314 multiplied by once again the temperature in Kelvin. Alright, so that's simple. The next question we'll ask is determine the Rms speed of the gas. Okay. Once again, we can use, now here we have two options. We can use either 3 kBT divided by M, or we could use 3 RT over capital M. Okay, and what we'll do is we'll do both these things. Alright, now in order to use the left side we must first find M, and M is the mass of each particle of the gas. Okay, now since we know the molar mass of helium, this mass of each particle is simply the molar mass divided by the Avogadro number. The molar mass is 4 grams, so remember you have to convert it to kilograms. Okay, divided by Avogadro number 6.02 times 10 to the 23. So this gives us the molar mass, and now I can write Vrms equals 3 times 1.38 times 10 to the minus 23 multiplied by 300.15 divided by 6, or divided by the number that you end up getting. So divided by this value of M that you will obtain in this one. Okay, so calculate this, see what you get. Now if we were to use the right hand side, the answer is actually much easier because we don't have to really calculate anything, all the values are given. So it is 8.314 times 300.15 and divided by M, which is again 0.004, and we can calculate the root mean square speed for helium. So calculate these two values and see what you end up getting. Okay, now part D of the question is determine the internal energy at 200 degrees Celsius. Okay, so if the gas is heated to 200 degrees Celsius, we'll find what the internal energy is. So U2 is going to be equal to 3/2 times 3 times 8.314 times the temperature at 200, which is 473.15 Kelvin, and you can calculate this number, and using this we can also find the change in internal energy, delta U, which is simply equal to U2 minus U1, and we can calculate that number. Okay, then part E we can ask determine the temperature at which the Rms speed is twice the value at 27 degrees Celsius. Okay, now the natural instinct here is to calculate all these values, is to start just plug it into the formula for VRMS and then find the temperature and all kinds of stuff. But there's a lot of times these questions are asked in multiple choice situations. So let's learn how to answer it. Okay, so we'll use the equation VRMS equals 3 times R times T divided by capital M. Okay, now our goal is to double the V. Okay, in order to double the V, if you look at this, for helium, capital M remains the same, R remains the same, and of course the number 3 is the number 3, and the only thing that will change is the temperature. Okay, so we ask the question, what do we do to the temperature in order that the entire number, this entire thing inside the radical becomes double? Okay, and the answer to that is very easy. Basically all you need to do is make the temperature 4 times what it was, because if the temperature is 4 times what it was, then the square root of 4 ends up being equal to 2, and that will give you the answer. So the answer is that the new temperature T should be 4 times the old temperature, which is 300.15, and that ends up giving 1200.6 degree Kelvin, and we can convert this to Celsius very easily. Okay, so keep that in mind. So you don't, there are a lot of times you don't really need to calculate all the stuff. Alright, so these are all the parts for the problem.